All right, time for another DraftPhysics.com, debatephysics.com, but we can't get any of these cowards to respond to any of the, reasonable arguments demonstrating that their physics is full of contradictions and nonsensical, almost silly, okay, declarations, axioms, statements about how the fundamental universe works. So anyway, we're doing Professor Dave's series on energy, I guess you could call it, motion, Newtonian style. They call it classical physics, but it's not Newton's physics. So they lie and distort what Newton stated and what can be reasonably stated to be what Newton understood how the universe to work. Galileo and Descartes also. And so they have this silly formula, 1/2 mv squared. It started off as just mv squared. The idea was is this living force, as it was called, was somehow not as direct or obvious as momentum, and that this is the real energy that something has, and that this is the quantity that's conserved in the universe. And so in spite of Newton writing a third law that said equal and opposite, in terms of what you have going in, you have to have coming out of an accident, an event, they've perverted and just said, well, we don't have to really believe that. And so anytime you transfer energy from things that have uneven masses, you get these ridiculous inequities. The gun being the obvious kind of example. 2,000 joules goes out one end, 2 joules goes out at the other end. The recoil of the gun has a feeble, tiny amount of energy. The bullet has 1,000 times more energy. And so theoretically, you could change how much energy is in the explosion by merely just changing how heavy the objects are you push with that energy. So if you push heavy bullets, you get very little energy out of the explosion. You push very light bullets, you get insane amounts of energy. And they take no account for how it doesn't work. It doesn't obey, it's not consistent with the law of the lever. So the lever proves it wrong. The ballistic pendulum, you can't collect any of this kinetic energy stuff. You can barely collect the momentum. Just a fact. You could make an argument about bowling. They say an 8-pound ball going 16 miles an hour has twice the energy, whatever that is, of a 16-pound ball going 8 miles an hour. Yet they can't demonstrate to be true. Professional bowlers can't make it happen. They can't demonstrate the existence of it because theoretically, if you think about it, the only way the energy can be transferred from the bowling ball is through a transfer of momentum. And it's this they don't understand. They don't understand that energy is actually transferred from one object to another object. So the 350-year-old idea of Descartes, and I think even Galileo, but whatever. Certainly Descartes made the statement pretty clear that energy is conserved in the universe. And, the simple idea is that that's all you can transfer is the mass velocity total. That number is always the same in the universe. The total mass and velocity is the same. So you could have more mass going slower or you could have less mass going faster, but you always have the same amount of that total in the universe. And the only thing that the bowling ball can transfer is its momentum. It can't transfer kinetic energy. So this kinetic energy is, in fact, never demonstrated to be actually moving through the universe. You can't land on the moon using it, and yet they keep claiming it's the truth. So the implication is it's not an irrelevant, sort of like Benjamin Franklin's mistake of plus and minus creates a couple of idiotic notions, like somehow voltage goes this way in a wire and amperage goes the opposite way, which is just idiotic. So you get a few little, silly things happen when you make mistakes. But this kinetic energy thing is all of particle physics is made out of it. There wouldn't be any Higgs boson without it. With it, is the only way they can create all these fake particles, because these fake particles just have to do with leftover energy. Neutrinos wouldn't be an idea, okay, without the kinetic energy theory. So a huge amount of particle physics is built on it. And you can even argue part of Einstein's theory, E equals mc squared, is made out of this mistake. And they won't account for the fact that it's an obvious mistake because it isn't shown in the evidence. And they won't argue that point. They won't show you it taking 25 times the fuel to move something 5 times faster. And they won't show you something going 5 times as fast doing 25 times the work. They won't show you because it doesn't happen. And they'll just talk their shit, pretend they have defeated all comers, pretend they have won some arguments, and it's all bullshit. And they're just too cowardly. Even when you offer them $2,000, like I did with this character, they still won't argue the argument. All right, so that's where we are. So this is the third video in his, I don't know which one to call it, elemental physics, classical physics videos. And so he's going to talk more about the nature of position, velocity, acceleration. That's what it's called. Part 1, definitions. So we're going to get into scalars and vectors again. So they have some notion that kinetic energy is scalar energy, whatever that could possibly mean to a rational person. It means it's speed without a direction. You have some kind of quantity called speed and you don't have a direction. Silly. Really. Silly. Alright, should be good to go.
Let's discuss position, velocity, and acceleration.
He knows a lot about the science stuff. Professor Dave explains.
In physics, we will often be asking questions like,
so there's the rocket again. So if you calculate the kinetic energy of the flame coming out of the rocket, all right, you'll get a number like, whatever, 250,000 joules. And then if you look at how much motion you're getting into the rocket per second, or per unit of that force, you'll see it's getting 3. There'll be no correlation between the two. The kinetic energy will not be creating an opposite reaction in the rocket. So just like the bullet, the theory completely fails to be consistent with Newton's third law. And if you calculate the momentum of the thrust, that is, you understand that it's a mass, a bunch of atoms and pieces of atoms flying out of the exhaust. Best to probably understand it as thrust in empty space where you're just using a gas, and that's a lot easier to calculate. But anyway, regardless, the momentums will be equal. And that's proving the point. Again, you can't land on the moon using kinetic energy. Use kinetic energy, all your calculations will be incorrect because none of them will obey the Newton's third law.
where is an object? Which way is it moving, and how fast?
So there's no point in saying it when you don't believe that which way it's moving is a concept, that it actually has something to do with energy.
To discuss the answers to these questions, we will frequently utilize the concepts of position, velocity, and acceleration.
And they'll do it in this perverse way where all they're really caring about is distance. So because there's a little nuance in gravity, because you're changing the velocity using acceleration, and you get to keep the previous acceleration, okay, as a future velocity, you end up with a quadratic increase. As you increase the amount of time you apply a force that's time dependent, you'll get the square of that time in terms of distance. And it's only because, yes, the first time you're pushed, you get to keep that push velocity. So in 1 second, you get 9.8. Now, you only travel 4.9 meters in gravity. You know, the first second, you only travel 4.9 meters. But the next second, you're going to get the free motion of the 9.8 in velocity. So you're going to travel 9.8 to 4.9s. You know. And then you're going to add, in the second another 4.9. All right, with another 9.8 in velocity. So now your velocity is 19.6, and you've traveled 4 times the distance. But it was only 2 units of time, and it's only 2 units of velocity, and it's only 2 units of weight, and it's only 2 units of energy. And they won't show you, they won't prove it's anything other than that.
So before we go any further, let's define these terms. Position is simple. It's just where an object is in space. Usually this is discussed with some kind of reference point or axes in mind.
So the point should be made is that Newton was rather aggressive in his Principia thingy, his opus, in making it really clear he's defending the idea that space is 3-dimensional and that there are 3 dimensions of space and there's absolute positions in that space. It's not just relative. It's absolute, and then you can be relative. But it's first and primarily absolute space. You can't undo the positions. You can't undo the distances. You can't pretend them away because something looks smaller when it's farther away. Doesn't mean it is smaller.
And we might express the position of an object as being some distance from this reference point in meters. Velocity is the change in position over time.
So this is the stinky part. That's not really what your velocity is. It's not your change in position, okay? It's how fast you are covering distance. And yes, the way we have to measure that, you know, we don't have some other way to measure it, so we use how far it traveled to decide how fast it's going. But the actual thing, the velocity, isn't made out of some distance-eating machine or some kind of machine like that, some mechanism like that. The velocity is an actual thing, okay, that makes it capable of moving because it has this function inside of it. So distance can fool you depending on how you're doing an experiment. How you're pulling energy out of something will decide how fast it appears or how much work it could appear to do. So you can roll something twice as fast, give something twice the velocity, 2 balls. And the one with twice the velocity will roll 4 times the distance. But it only rolls 4 times the distance. That is because you're taking the energy away. You gave it an acceleration. It's going to now lose its velocity as it rolls. And if you apply friction evenly, all right, the fact is the thing with twice the velocity, it's the same gravitational rules. And the friction won't be the same. There'll be less friction the faster it's going. So the faster object's going to take longer for it to lose its energy because it's losing it per unit of distance more slowly because of its higher velocity. So these are just facts that they couldn't care less about and won't address because they're cowards.
So if this object travels 5 meters in 5 seconds, it is traveling at a velocity of 1 meter per second. And
right, and gravity gives you 9.8 meters per second, 1 second. 9.8 meters per second, per 1 second, per 1 second, not second squared. So again, Newton never said second squared. It's not his physics.
Acceleration is the change in velocity over time. So if this object starts at a standstill and over 5 seconds gradually speeds up to 5 meters per second, then it is accelerating at 1 meter per second per second.
So this is the jargon. 60 miles an hour per hour, per hour, per hour. I mean, how many times you're going to play this game that you're going to, pretend that the concept needs a squared second. There's no squared second involved. It's not, you can't square seconds in the first place. Conceptually, it doesn't make any sense. But because it's per second, doesn't give you a right to say, oh yeah, that means second squared. Because it doesn't, because it's per 1 second, 1 unit of time, and it's per 1 unit of time. It's 1. 1 times 1 is 1. Cheater.
Or 1 meter per second squared. So that's how we define position.
Right, so that's an axiom, and it's just used that squared seconds will be used later to find an excuse to multiply seconds times seconds and come up with some kind of like 8 times 8 or 17 times 17 when there isn't any such number involved.
Velocity and acceleration. Now let's discuss each of these in more depth. When we talk about position, we could discuss distance or we could discuss displacement. The difference here is that distance is a scalar, while displacement is a vector.
So again, how does it make any sense? No, of course it can't make any sense. Distance, displacement, how can you use these two terms that are going to describe the same thing and then pretend that somehow the distance isn't a known thing and somehow the displacement is a known thing or a measurable thing? It's just nonsense.
Let's say you and your friend get dropped off by the school bus at this intersection, and your house is here. Your friend begins to walk down the street and up the driveway, like a normal person. But you find yourself so overcome with excitement to play video games that you decide to plow through the yard in a straight line to the door. Your friend has to walk 20 meters down the street and 7 meters up the driveway for a total of 27 meters.
And that's what he actually has to travel. So, there's no point in talking about him being anything other than that's what he did. Okay, he actually has to navigate that distance. So this idea that there's something called a displacement, which means he didn't actually have to do this work, or he didn't do this work, is bullshit. So this just has to do with whether there's a force coming at you from a direction. And again, that can be understood, that if you're moving this way and you're pushed sideways, you're going to travel a vector that's going to be different, and then you're going to actually travel a different velocity.
Using the Pythagorean theorem, we find that you only had to walk about 21.2 meters, and you probably got there a little sooner. What we can say is that you walked different distances, which are represented by these scalar values, but you both had the same displacement.
So like I said, this would only matter if this 7 meters and this 20 meters, we were talking about forces that you were being pushed by, or forces that you were resisting, that you were having to move into. So that's the only way it would make any sense if these were hills. So if you were talking about these being hills, then this conversation could mean something, but it can't mean anything just as traveling distance.
Because you ended up in the same spot, at the front door. This vector, which follows the straight line path, is the
So if you're going to measure how much altitude did you gain, yes, you both gain the same altitude. If you thought of it as altitude, the 20 meters and the 7 meters as altitude. So it would be the same. Yes, you both ended up at the same altitude. So overall, you fought the same amount of gravity. But it doesn't change the fact that you're going to have to walk more steps doing it one way than the other way.
Placement vector for both of you. And we can report your position with x and y coordinates like this, 20, 7. Or we could report the magnitude of the displacement vector, which will be equal to the shorter distance you traveled, and calculate the angle off the horizontal using trig functions if we desire, in order to report the direction of the vector. Next, let's look at velocity, which is the rate of change in position. Most people assume that the words speed and velocity are synonyms.
Yes, most people are rational, I guess, then, and they recognize that there's no way you can get a speeding ticket if you're not traveling in a direction. You can't get one for spinning in a circle, just yeah, can't get one for that.
And in everyday language, they are. But the difference in physics is that speed is a scalar and
so meaning nothing, right? So it's a scalar, meaning somehow it doesn't have a direction. It's just some sort of velocity term that doesn't have a little arrow over its head, meaning it's actually a velocity in a direction. So the fact that they're saying it is a velocity, you'll use a v to denote it. And because you're going to claim it's scalar velocity, that somehow it doesn't have any correlation to reality is what the bottom line is, because it doesn't. It's just completely fake nonsense. You can't have speed in no direction.
Velocity is a vector. If a group of kids are playing hide and seek and they all run away from the seeker in different directions, it is possible that they all run at the same speed, because speed only has magnitude and no direction.
So whatever that could possibly mean, they're all moving in a direction. They can't have speed without having their direction. So there's no way to calculate their speed or to understand their speed or anything for their speed to mean anything. So to claim that you can create this fake thing, this fake property of a speed in no direction is just crazy. It's silly. It's stupid. It's incomprehensible mush. All right, might as well do a little drawing here. All right, so instead of that example, you could have just said you're going to have a place and individuals are going to run from that place, okay? And you could argue that they're in a, gated community, okay? And so we're going to have two contestants, all right? One of them's going to weigh twice as much and go half the speed, okay? So you could say this one's going to weigh 100 kilograms and it's going to go, 8 miles an hour, right? And the other one's going to be 50 kilograms, okay? And it's going to go 16 miles an hour. So it's sort of like the bowling ball example. And the argument is they're going to claim that this one has twice the energy. Okay, this one has twice the energy. So this has twice the kinetic energy that this guy has. So even though the argument could be made is that they're used the same energy, they're working as hard, that one of them has twice the energy. And the only thing that can be true is that this wall, you could say, could be made out of different substances. And depending on what the wall is made out of, okay, you can break it with how you apply force to it. So you can certainly understand that if I concentrate force by putting an arrowhead on an arrow, that it's more effective in penetrating a surface. And so changing how much surface that actually has to absorb the energy you're applying, you could understand, yes, the more surface you spread your weight over. So that's another thin ice argument, that if you lie down and slide across thin ice, you got a better chance of getting across than if you are stepping on thin ice. I've done this experiment. Yeah. to get to work. Anyway, and then the other argument can be made is that substances are also velocity sensitive. That is, if you hit some things with a very high velocity, a very small momentum, but a high velocity, the fact is you can fracture them because they can't absorb the energy at the speed you're applying it. That is, the surface can't transfer the energy. So we know that pretty much motion is transferred in objects at the speed of sound of the material. So a piece of steel has a pretty fast speed of sound, a few thousand miles per hour. And And if you hit the steel, theoretically, with something moving faster than that, the steel will actually start to deform rather than absorb the energy and transfer it as motion. So the other end of the steel won't move as much as the end you hit because it starts to screw around with the arrangement of the atoms instead of transferring the energy. And the more aggressively you do that, the more you disturb the surface. You can actually hit steel with a bullet, for example, and you can dent it, and you can break off pieces, and the bullet's pieces will also reflect off of it because it can't absorb the energy. It can't send it to the other side of the steel. It can't make all the steel move because it can't transfer the energy fast enough, as fast as the energy's been applied. So speed has advantages in breaking things. So if you're not thinking about transferring energy, but you're just thinking about using energy to break something, they're two different things. And the fact is that speed does help you break things, but it doesn't mean you have more energy. It means you applied it differently. So you can go into arguments about karate and different the physics of different applications of energy in conflict or contact, and understand that it matters how you apply energy. How you apply can get you a different result. But if you're going to use a fair example, you don't shoot bullets at bowling pins, because the bowling pins won't absorb the bullet's energy. The bullet will penetrate the pin, do all kinds of different things, but you're not going to get the same kind of test. Whereas if you just roll a ball that's 16 pounds at 8 miles an hour, or 8-pound ball at 16 miles an hour, you'll have a fair fight. The fact is, it'll demonstrate that there's no difference in the amount of momentum, and there's no difference in the amount of energy. The same amount of total mass will be moving. You won't be able to claim one of them has more joules of anything called energy, because the output will not be consistent with that theory. Alright, back to the video.
So they could all run at a speed of 3 meters per second if they are quick little devils. But each kid would have a unique velocity vector that has a magnitude of 3, but also describes the direction of motion, most likely using the seeker standing still as the point of origin.
So he didn't say anything there at all. So how did that show speed? How did it show kinetic energy? It didn't. It was just a nice straight vector line indicating this is your magnitude, and you gave it a direction. So show me the magnitude without a direction.
Velocity vectors will be extremely important as we move forward with kinematics, where we will study the motion of objects. In general, average speed can be calculated by taking the distance traveled by an object and dividing by the time it took to do so. So if you walk 85 meters in 46 seconds, you are walking at an average speed of 1.85 meters per second.
Right, and frankly, you could argue that that gravity is an average. Okay, so, and let's see, how do you even state that? Because it won't be your average speed. It'll just be what you're gaining as velocity. So it isn't an average. You only travel to in 1 second you travel 4.9 meters. So obviously your average, okay, wouldn't be 9.8 meters per second. But that's what your net end velocity will be, is 9.8.
To find average velocity, you can do the same, but you would have to divide displacement by time. Lastly, we have...
Why? So you didn't show an example of why I have to do that. But anyway.
Have acceleration, which is the rate of change in velocity. This is always...
So it's just a velocity. You're adding velocity or subtracting velocity. Acceleration isn't some special thing. It's just adding velocity or subtracting velocity.
It's a vector because acceleration must occur in a particular direction. If you are in a car that is standing,
I mean, velocity must be in a particular direction. So again, it's just it doesn't make any sense. Speed has to be in a particular direction. So there isn't any other way to look at it than to say, yes, you're traveling a certain speed or velocity, and you're doing it in a direction. And there's no other. Again, they could say that a train has a certain amount of kinetic energy. It doesn't have a certain amount of kinetic energy in anything other than the direction of the tracks. The energy isn't some other direction.
still and you press on the gas, the car will begin to move forward with a fixed acceleration. It might accelerate slowly, so the vector may be on the shorter side, but this constant acceleration will cause the velocity to increase at a fixed rate. Let's say an additional meter per second every second. So over 5 seconds, it will reach a velocity of 5 meters per second. Let's say you see a skunk in the middle of the road. It's your most favorite animal, so you slam on the brakes. We can describe this as a deceleration, which is an acceleration in the negative direction.
It's just a change in your velocity. Again, that's all you're doing. You're just changing the velocity by adding or subtracting.
Since you are
Velocity.
going from a moderate speed to a standstill in a very short amount of time, this vector will be quite long and pointing back towards the origin. Now we understand distance and displacement, speed and velocity, and acceleration. And
So all you need to understand is, yes, it's arrows, and you just say, well, velocity is the length of the arrow. And if you add velocity, then you have you're lengthening the arrow, you shorten the velocity, you take away some, you're getting rid of it. It's just plus and minus arrows. So that part there's no problem with. It's some idea that there's a magnitude without an arrow. That's the bullshit of the scalar.
we can categorize these as being either scalars or vectors. Before we finish, let's look at a moving object like this marble rolling to a stop and visualize.
That's a good example, just because their physics is sort of arguing that the friction is linear. That is, per inch, it's always the same amount of energy being lost to the surface. That the ball, as it rolls across the surface, if you thought of the surface as being a bunch of bowling pins that it was going to wobble and knock over, you could understand that the faster it's going, the less contact it has, okay, and the less energy it's giving to those pins. And the slower it goes, the more gravity's pushing it in, the harder it hits the pins, the more it hits them, and the more energy it transfers. So friction has a curve, and it starts off being, well, I should do it this way. The faster your velocity, well, yeah, the higher your velocity, the less the friction, and the lower the velocity, the higher the friction in terms of how much energy you're transferring.
All three of these vectors as the object moves. First, with displacement, this vector.
So this is irrelevant in this case. There's no displacement. There's just distance.
Will just elongate as the marble rolls and will span the distance traveled. For velocity,
Yes, it's going to be the distance. That's right.
the vector will point forward as the velocity is positive, since it is moving in the forward direction. And the vector will move along with the marble, but it will decrease in magnitude as the marble.
Right, but it won't decrease linearly. It's going to be going half its speed 3/4 of the distance. So that's really important to understand, just like gravity. You're going half your speed when you travel. Say you're going to travel this distance. In gravity, when you're falling, you're going half your speed here, not here. Here. Yeah. Yeah, after the first second, you only traveled 4.9. You're going half your speed right here. And all of this doubles your speed. This huge amount of distance is where you're going to double your speed. So it's not that you're going half the speed at half the distance. So they can't even figure out this simple physics, that friction isn't always the same no matter how fast you're moving across a surface. So when you're going fast, you're giving away a little bit of energy to friction. When you're going slow, your gravity has plenty of time per inch to push you in. You're way more per inch. So you weigh less per inch the faster you go across a scale, for example. The faster you go across, the less the scale can register your weight. And the slower you go across, the more likely it is it can register your gravitational weight. So you can just understand that the more you're pushing into the surface per inch, the more energy you're going to lose to the friction. And the less you're pushing into the surface, the less you're going to lose. So maybe this is the better example of just dropping something next to a surface. And you can understand that if I'm pushing with a constant force, as it's falling fast, it's this much distance, okay, for the same amount of pressure, that'll be this much distance. So this small amount of area gets the same pressure from gravity, the same 1 second, as this whole giant piece of distance.
Slows down until eventually disappearing when the marble comes to a rest, where it has 0 velocity.
Right, and now the table has the velocity, so that how people can't understand it. Yes, that's the simple principle that Descartes was talking about. And even though they didn't really understand the concept of heat and all that kind of stuff, that's what they were starting to talk about. This idea that you could smash 2 pieces of clay into each other and the clay would have deformed. And the deformation would mean it goes everywhere. It has to deform the atmosphere. It has to change everything. And that's where the motion goes. So you had motion in one object, and you put the motion into some other object. Well, we don't see the table move, but we all know it is moving. We know that the table's vibrating, and that's where the energy of the rolling ball went. It went into moving molecules on the table. It knocked pins down.
And then for acceleration, the
friction pins.
Vector points in the negative direction, since velocity is decreasing or becoming smaller per unit time.
Right, and it's not doing it in a linear manner. Okay, so it's losing less, it's doing less decelerating as it travels the first 3/4. So this distance is about right. The idea is it's going half the speed here. Oh, shit. The mouse stopped working. That was a little spooky. Here. That's where half the speed is. Not here in the middle. Here.
But it will be constant in magnitude, since this is a constant deceleration.
So it's not constant. So that's again, it's not a fact, Dave. It's not the truth. It's not how things decelerate. They don't do it in a constant way where it's the same amount of deceleration per inch of distance traveled. It's not true, Dave.
Due to friction from the surface it's rolling on.
It's flat earth stupid, Dave. Yes, the surface can absorb. You can make the surface very rough and it absorbs the energy more quickly, but the same concept will still be true, is that you can overcome the friction by increasing the velocity and reducing the amount of pressure per inch.
We can view all 3 of these at once.
They're using the concept is it's using gravity to create contact. And the contact is like for electricity. A little tiny bit of contact, you can only send a little bit of wattage through the wire. You have a much better contact, you send a lot more electricity through the wire. And it's the same argument here. The contact, the pressure being created by gravity, is deciding how much contact there is with the table. And the faster the ball rolls across the table, the less energy the table can absorb.
Once, just to drive things home. Make sure you understand the magnitude and direction of each of these vectors at each moment in time.
And I mean, I'm just suggesting that the fact is he's misinforming people by claiming that this isn't directly, the amount of energy being transferred is directly proportional to the amount of force being applied, pushing the ball into the table. And that is changing. It's constantly changing. The amount of pressure felt by the molecules of the table is increasing as the ball goes slower and slower.
Let's check comprehension.
Do I want to sing the "fuck you in the ass" song? Yeah, it's just such bullshit, this quizzing. Ugh. It's just such a, it's the last thing in the world I would sit there and waste people's time doing is, rubbing it in their face. Oh, look, you still can't do it right. Fuck you. Alright, jump ahead of this crap. Why not just have that as a separate piece of paper?
Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content.
Oh, fuck. And people do. So he's doing it wrong. He just stated something that isn't true, that somehow friction is a constant drain. It's equally draining per inch when it's not. And it's a critical thing to understand because it just demonstrates the fact that kinetic energy is a fable. It's just nonsense. It was never true. It was never shown to be true with good evidence. And it's a nonsense on its face. I think it doesn't take 25 times the fuel to move anything 5 times as fast. 5 times the fuel, 5 times as fast. 5 times the speed, 5 times the impact. Not 25 times the impact. Just absolute bullshit. And such. Okay, so done with that one, I guess. So we'll just keep going through them all. And all you can say is they're just cowards. They're going to lose the argument because they have no evidence. The Mythbusters did one experiment where they showed basically the truth. Okay, they crashed a car at 100 miles an hour, same car, crashed at 50 miles an hour, just twice the energy, twice the crushing of the car, and that truth will be always true. There isn't any increase in energy as you change from a big V to a little m. Big V, little m is somehow more energy than big M and little v. When no, it isn't. 1,000 atoms going 1 mile an hour is the same ability to apply pressure as 1 atom going 1,000 miles an hour. Same thing. Same energy. You can create both of those events with the same energy, and both of those events can produce the same motion in the universe because momentum is conserved. Kinetic energy is not.